Okay, so people will join in if they want. Now let us start, those who are waiting for last 5 minutes. Today we will be discussing and ending our discussion on operating system, and I will be discussing on the topics from where you are likely to get questions, right? So today in our discussion, we will be having more or less four things. One is the memory management, one is the disk management, and then we will go to the protection and security part of your operating system. Now, in protection and security, we don't have much, so hardly only few like the prominent names from where they can ask that what is this, what is that. So those things we will discuss. Now, let us first start our discussion on the memory management part. See, memory management is a topic which you have gone through in your COA, Computer Organization Architecture, and you have also gone through in operating system, right? So now what we will discuss? First, let us discuss that what exactly we do using the memory. Very simple, we store some data, right? Now, if I say that I store information, it is not correct, because in your memory, it is stored in very basic level, which is not at all a data, right? Which is not at all an information, which is a data, which is not logically fine, right? So now, suppose if I want to store data, suppose I want to store the word apple, right? Suppose I want to store a word apple. So when you are trying to store this data, this is a meaningful data, right? So I can say that this particular one is a form of information, right? Though itself it is not any information, but though we can. But when you try to store this in your memory, you never know at which position, which particular alphabet will go and get stored, or the total thing will get stored at once or not. So based on that, we have different type of storage, means categories of storage, right? Now, why we are storing memory management here, why we are studying it here? Because memory management and any type of resource management is a primary job of our operating system, right? So how much space is available for data storage? How much place is already allocated to some storage? All these are maintained by your operating system, right? Now, first we will understand that what type of memory exactly do we want? Now, what do you mean by this question? See, all of you are having different type of memory in yourself. If you think that currently you are studying operating system, so like previous 2-3 days of classes, you are studying operating system. So if I ask a question and if you attended it solely, like in means attentively, then you can answer. You have studied DBMS. Same person has taught. Suppose same interest you have, but do you remember everything of DBMS right now? It is not so much likely, right? So you know, but you need to revise. You can say, I need to revise, or I need to go and check it once. So these things you can say. Now see, what is the difference? Something which is present in your memory and ongoing, and something which is in store, whenever you need, you can just give it a call and you have the access to it. Suppose you have compiled design in your curriculum, but that thing you have not learned it yet. That means that is in store of yours. It is not yet taught to you. Similarly, there can be another type of data that you have. Suppose ABCD. I am writing memory management. So I am using the alphabets ABCD, right? I have learned it many days back. You also have. But did you forget? No. If you want, you can use them. Right? So different type of storage you also have in your memory. Similarly, the computer also needs different type of storage. Like if I say that A equals to A plus 5 and B equals to A into 2, right? So what do you mean by that? Students, no need to give attendance in the chat box. Your attendance will be automatically calculated if you are present in the class with your enrollment number. So if I have two instructions in my program, line number 1 is calculating the new value of A, whatever was previous value of A is getting +5. The value of B is having the calculated value of A into 2, right? So when this program is written and stored, not in execution, it is in one type of memory. When you start executing, execution means if you are running, like if you are using GCC compiler, then using the program name. If you are using Java, then using program name, anything. You are executing the code. At that time, you are into a different sector of memory. Suppose this A, this value of A, this is used in line 1. Also, this is being used in line 2. Means this is frequently being used. A is the value which is frequently being used. So for that also, I have another set of memory, right? So if I go through all these states, I can derive a hierarchy of memory that we have in our computer system as storage, a hierarchy. So how it looks like? It looks like a pyramid structure where on the top of it, we have the registers. Then we have the cache. After cache, we have our main memory. And at last, we have our secondary storage, right? So this particular one, if we give it a shape of a pyramid, why I am giving it a shape? Because, sorry, this particular area is your storage space. So as you go down in the pyramid, your cost is decreasing. As you go down, your storage, sorry, the cost is minimum at the bottom level and maximum at the top. The storage is minimum at the bottom, maximum at the bottom level and minimum at the top. And the capacity of working, the working capacity is most, or we can say the working capacity, you must write. Capacity does not mean storage. Storage is different. So this is your memory hierarchy. Now, if you look at the memory hierarchy, you see this particular one, the registers are associated with the processor. There are different names of registers, like we have accumulator register, we have data register, we have instruction register. Registers are very, very small in size. They are able to store a very less amount of data at a time. And this one is directly communicating, or rather it is associated on the processor only. This is not a part of another separate memory storage. It is a part of your processor. Next is the cache. Cache is a connection between, this is the processor and the main memory. Right, so here lies your cache. So what is cache? These type of data, or suppose the data like the alphabets I am saying, which I'm frequently using. The data which I'm frequently using or I have recently used, that data will get stored into cache. Understand, memory is a purely storage device. And the processor is having greater clock speed. You are investing money behind your processor to get better processing speed, right? So processor is fast, memory is not that much fast. Memory is a storage device. It does not operate on like processing any data, right? So when they communicate, the supply of the data from the memory is very, very less. Clock speed of memory is less. So it can be operated through a clock. So it is less. So what we do, in spite of searching memory, memory size is more. So if I need to search it in a memory, then the search time is more. So what we do, we fetch some data from main memory to cache. Which data? Some data which are frequently used and recently used. Frequently means it will always be recently used. So those data will be stored in cache. Now, cache is a smaller space, so the processor can get the data fast. Search space is small, right? So it can get the data fast. Next, it comes to the main memory, where actually we mean the RAM and ROM, right? Now, when we come to main memory, a part of RAM is present in your cache, right? So RAM is again of two types, SRAM, static RAM, and dynamic RAM. If you have forgot these concepts, then please go through them before you start preparing, right? So SRAM and DRAM, a part of your SRAM is your cache, right? What is SRAM? With time, the data will not get lost until and unless you are switching off the power, right? And what is DRAM? DRAM is made of capacitors. So with time, charge will decay and the data that is being present can get lost, or portions of data will get erased, fine? So a part of your SRAM is your cache, fine? Now, when you come to main memory, the search space is more, right? So you can store more data. So which type of data you will store? The data which is currently under process, you can store them, and a part of data which will not be deleted with the power off. What type of data is that? Your ROM, read-only memory. Now you can say read-only memory, the concept is we cannot erase the data, but there are ROM types like EEPROM, electrically programmable read-only memory, programmable read-only memory, electrically erasable programmable read-only memory. So these are the types where you can change the data, but with a bit of effort. Like in RAM, if you switch off the data, then only the data is gone. But in case of ROM, to lose the data or to erase the data, we need to give a lot of effort, right? But data can be erased. So that is about your main memory. Now, when you come to the secondary storage, suppose you have a grocery shop, right? So you have a lot of items there. Now, which type of items do you keep in the grocery shop in your front rows? The ones which are the highest sellers, right? Now, don't you have backup of them, right? Suppose a packet of biscuit you have. So there are 10 packets of the same type of biscuit, right? Suppose Oreo, I have 10 packets. Don't I have more? I have more in my store, right? So it's like a go down where I have a lot of data, but everything cannot be accommodated in the front row of my grocery shop, right? So that concept of go down can be compared with the secondary storage. Fine. So secondary storage can be associated within your computer, or it can be an external type of secondary device. Fine. So we have the concept of magnetic tape, magnetic disk. Nowadays we have hard drives. So those all are secondary memory, right? Which are not directly accessible by the processor, but it has to go via the main memory in order to reach to the processor, right? This is the concept of your memory. Fine. Now, next thing that we have is the data storage. Data storage means memory allocation, right? How, when I'm storing A plus B, where the A is going, where the B is going, where the plus is going, and what is happening, that is your memory allocation. You have two types of memory allocations. One is the contiguous. Again, you are preparing for placements. If you are preparing for placements, then names you must remember. and what they do, that you must remember. Nobody is going to give you problems like solve this problem. They can give, but that is a rare case. But generally, they will ask question from the names, right? So contiguous allocation and non-contiguous allocation, right? So now let us understand that what are they. Contiguous allocation, non-contiguous. By simple English, we can understand that contiguous means side by side, one after the other, wherever there are vacant places, I can store data. What is non-contiguous? If suppose contiguous means the way you are giving exam, you have a sitting plan, so roll number by roll number you sit, right? So that is contiguous. What is non-contiguous? Suppose we don't have a like in midterm, so fine, we don't give you the seating plan. So the section allotted room, you will go, suppose B3LG 3.1. You go there, 50 people are allotted. So any place you find and you can sit. Suppose there are some vacant places. So what we will do, suppose 1 to 50 has come. So 51 to 60 we call and we ask them that wherever you find a place, you can sit. Now some people will not get a place. So then next allocation will be done to them. Like 3.2, they will go and sit. That is a non-contiguous allocation. So wherever we find an empty place, we put people there and they can adjust and sit. So both allocations are having their advantage, disadvantage. Generally, we deal with memory addressing, right? Whenever memory storage, this arrowhead means what? This is maximum. This is increasing. When I am going down, it is increasing. Storage. Capacity of working means the working capability, how fast they can work, that is going up. Means cache is less faster than register. Main memory is less faster than cache. Cost, whenever it is highly working, more efficient, the cost will increase. So register is most costly. What is confusing here? Your arrowhead must indicate that how it is increasing. Right? Okay. Next is, when we are dealing with memory address, contiguous allocation is simple and easy to use. Right? One after the other, like arrays, they will be stored. But in case of non-contiguous, we have to keep a pointer. Right? You have the concept of pointers. So in non-contiguous, we have that. Whenever a data is getting stored, the next data's pointer will be stored along with that. So we can give it a name like a linked list, right? Simply we know, so we can give it a name like that. Now, in case of contiguous allocation, in case of contiguous memory allocation, suppose, so we can say that an example can be array, and this one, an example can be, linked list, right? Fine. Now, suppose I have a 10 KB of memory storage where 2 KB is already used. 4 KB free here, 4 KB free here. But in between, this 2 KB is already in use, right? This is a contiguous allocation. Now, suppose a process comes P1 of 5 KB size. P1 is a 5 KB size, needs allocation, needs some storage, right? In this structure of contiguous allocation, I have free space as 4 plus 4, 8 KB. My request is to store a 5 KB file, but as it is contiguous and in between this 4 and 4, this 2 KB is already occupied, I cannot allocate this 5 KB space. cannot allocate this 5 KB space. Right? Understand the problem. Contiguous allocation means continuously you should have 5 KB space, then only you can allot. Right? So if I have a process due to the lack of contiguous or non-contiguous storage, if I cannot allocate, yes, Galvin book can be used, but if you have concepts, then only you go for a book, right? Or else the book will be of heavy pressure for you at this point of time. If you want, you can always refer Galvin, that is the best book available. Now see, I have space more than enough that is required. 8 is greater than 5, right? But I cannot allocate. Why? Because it is not contiguous. What is the type of problem? I cannot allocate the process. I cannot allocate the total process. And this is named as fragmentation error. This is named as fragmentation error. This we call as external fragmentation. While you are attending the class, please note few points like the names that you must learn if you haven't. What is external fragmentation? In one line, if I have available space or due to lack of space, due to any problem, if I cannot allocate a total process cannot be allocated due to lack of space, then I say that it is external fragmentation, right? Next one, if I have non-contiguous allocation of the same type, I have a 10 KB size memory and my 2 KB is in use, same like story. So 4 KB here and 4 KB here. And my process request is of 5 KB size. It is non-contiguous, so I don't have to be continuous in my storage. So let us store the 4 KB here. Let us occupy the 4 KB on the left-hand side of the occupied. And here, let us store the 1 KB. Right? So 4 KB plus 1 KB, 5 KB is allotted. Fine. So this particular advantage we have in our non-contiguous type of allocation. So you can see this is a very, very common type of means very much easy and very much efficient to be used for, right? So this particular type is named as the non-contiguous type of allocation. Fine. So example, you can have this linked list and here it is array. Now see, when we go for contiguous allocation, next let us come to contiguous allocation. Again, contiguous allocation can be done in two types of availability. One is fixed size partitioning of your memory and one is variable size partitioning of your memory. Fixed size and variable size partitioning of your memory. Now let us understand what do you mean by that. Suppose I have a 10 KB space. This 10 KB is divided into 5 KB, 2 KB, 2 KB and 1 KB. If this is my case, then it comes under variable partition, right? If suppose I have a process of 4 KB, this is my request coming in for storage 4 KB. So where I will store, if I have a size more than the requested one, I will always go there, I will store it contiguously. Now, this 5 KB will be utilized. So here, I will adjust my 4 KB P1. Here, I will adjust my 4 KB P1. Now, this place is vacant, this 1 KB. So this one we call as internal fragmentation. We will learn using other examples also, but just to have your idea, within one partition, if some place or some space is vacant due to the allocation of lesser sized data than the available size, then that unused space is called as internal fragmentation. And what is external fragmentation? Due to lack of space or contiguous type of allocation, if we cannot allocate a total process, then we call it as the external fragmentation. So internal means within a partition, and external means it can be within a partition, it can be like in the total space of your memory, it can be anything, right? So internal and external fragmentation, these terms are important. In case of fixed size partitioning, if I have like 10 KB, then either it can be of 5 KB, 5 KB, or it can be of 2 KB of 5 partitions. 2, 3, 4, 2, 2, 2, 2, 2. KB is so 10 KB, right? So fixed size means all of them, or fixed size means we can say that like all of them are having same size, but one concept you must know, that fixed size does not always mean that partitions are of equal size always. This may not be the case always in fixed size partition. Fixed size partition means the memory is already divided into some categories, like this 5, 2, 2, 1. This can also be seen as a fixed size. Means if I have a memory and before any allocation, I just partition them, like suppose 5, 5, 6, 6 and 1. If I partition them into fixed amount of size and then only I have to do the allocation, it is named as fixed size. So fixed size can be of same size, equal size of every partition. It can be of different size also. But in case of variable partitioning, I only have one space given where the total space is 10 KB. Now, depending upon your demand, this is your actual variable size partitioning. Depending upon your demand, anywhere you can place the data. There is no fixed partition. So fixed size partitioning means this type of concept. Not always all will be of same size, but they can be of same size. They may not be of same size, but they are fixed in nature. You cannot change them. They're like this one you cannot make 6 and this one you cannot make 5. This you cannot do, right? So if this is 5, this will remain 5. So where whatever data you have to adjust within this 5, or else it will be either internal or external fragmentation, right? So this is your internal and external fragmentation and fixed and variable size partition. Any problem till that? Do you have any problem till this point? Fixed size can be of same size of each partition, can be different, but sizes cannot be altered. Variable size generally means total space is given. According to your requirement, you can like alter places and save data, right? Is it clear? You have any doubt, or else we will proceed towards the next part? Next is the algorithms for assignment or storage. assignment or storage, anything you can say. Right? Suppose we have a memory (50, 150, 300, 350, and a big one, suppose 600. This is a memory storage that we have. This is partitioned. Now using variable partitioning, we will allocate data. Now first let us say this one, this one, this one. These are already taken. These are already filled, right? Let us see the requests that we have. P1, 300, P2, 25, P3, 125, P4, 50. This is the request that you have got, right? Now, the first algorithm that we will study, so this is my question, right? This is my available space. This is my requested data. Now, how can we allocate, right? So first we will go for first come, first serve, right? So what is it? The first available space that you have will be allocated to the first request that you are getting, right? This particular type of strategy in your allocation is named as the first fit algo. Okay? Fixed and variable size. Yes, I'm repeating. Just let us repeat it once. Fixed size partitioning means before your allocation or any request entertainment, your size of the partitions available for storage is already defined. So you cannot change them or alter them while you are storing. Suppose if you have, as an example, I have given 55661. If you have, suppose a request 7, so that you have to adjust within any one partition. You cannot use this 6 and this 1 of 7. You cannot do that in fixed size. So this will be an external fragmentation. You cannot allocate, right? So it will be in fragmentation. What type of fragmentation? Total process cannot be allocated. So it is a external fragmentation. If you have a memory space given, suppose 10 KB, but no divisions are made. So based on your request, you can adjust your allocation. So you have a request of 7, right? So suppose from the index 2 to index 9, I am taking this space of 7, right? So that you can do, or else you can start from 0 to 6 or 1 to 7, right? So that is variable size. Fine, you can adjust. Fine. Now, in this particular case, the first fit algo, request is given, available space is given. Now see where I will allocate. If I am using first fit algo, where I will allocate. Suppose let me draw it once more, or else it will be a bit clumsy. So 50, 150, 300, 350, 600, right? Already taken ones, I will just shade them. These three are already taken, right? So first come, first serve, if space is available. So first come is 300, right? So where this 300 will get stored? Where your P1 will get stored? Can this 150 allocate your 300? Obviously no. So where it will get stored? In the 350 range. It is variable size. So I can just take my P1 here, which is of size 300, variable size partitioning to. I can take one portion. So how much left? 50 is left, right? Then you have P2, right? This is first come, first serve. So whenever a new request is coming, like P2 has come, you will always start from this direction, wherever you find empty place, right? So P2 is of 25 size, right? So where P2 will get stored? First you have 150. So can 150 accommodate 25? Yes. So here I have my P2 with space 25 allocated. So 125 left. So this is adjusted, this is adjusted. Next you have P3. So 125 is requirement and 125 is left. So very good. Let us give P3 here. Next you have, so this is also done, P4. P4 is of 50. Very nice. Here 300 is allocated out of 350. That means 50 left. So 50. Right? So is there any process who is unassigned, unallocated? I have used all the spaces that I had based on first come, first serve. But is there any process which is untouched? No. Everyone is adjusted. Right? So there is no external, internal fragmentation. There is no external fragmentation, right? Now you can ask what is internal. We will just understand. Let's go to the next algo. Best fit. So fast fit means you will start from your left hand side. Wherever you find an empty place, you will try to adjust your process if the size is less, right? Means obviously 200 cannot be accommodated within 50 size space, right? So same address space. Let me just draw it quickly. So 50, 150, 300, 350 and 600. Okay, this is my space. Okay, so these are already allocated. Now this is best fit. So we will have to keep in mind least fragmentation. Least fragmentation, right? Which type of fragmentation? Internal. That means 150 will, if I have an option of accommodating 50 versus 125, then 150 will be accommodating 125 always, right? So less number of wastage. Internal fragmentation means wastage. So what request I have? P1 is 300. Okay. I don't have any option. 150 cannot accommodate 300. So, okay, 50 remaining. P1, P2 to 25. So here I have 50 empty space. Here I have 150 empty space, which is the best fit for 25. I have two vacant spaces. One is 50, one is 150. I want to allocate a process of size 25. So which one is best fit? Tell me. Which one is best fit? Which one, if I allocate, then the wastage will be less. If I allocate in 150, then 125 wastage. If I allocate in this 50 range, then only 25 will be wasted. So which is the best fit? আরে এটাও বলতে পারছিস না তোরা, you are not able to say this much? Only one or two answers I am getting. বাকিরা কি জয়েন করে ঘুমোতে চলে গেলি? You are having a nap? Okay, so now I have got some answers. Fine. So we will be accommodating into 50 because this is having a loss of 25 and this is having a loss of 125. So obviously I want a loss of 25. So here my P2 with 25 is, sorry, P2 with 25. So just I will make another partition. This is my P2. Okay, 25. So again another 25 is remaining. Okay, so it is becoming thick or like that. Okay, next P3 125. I have 25, so P3 cannot be accommodated in 25, right? So 125 means nice, 25 remaining. Now the problem occurs with P4 where I have 50. Here I have 25. Here I have 25, right? So can I accommodate it like this? Can I accommodate it like this? 25 remaining here, 25 remaining there. One process, if I accommodate it like this, it will be a bit problem, right? So what you have to do? This becomes an external fragment, sorry, these two becomes internal fragmentation, while P4 having size 50 is the external fragmentation, right? So as it is variable size partitioning, then I am storing both of them together within 350. If it is fixed size, then only one. Fine. So this is an external, these two are my internal fragmentation and this one is my external fragmentation. So even if the name is best fit, first fit can allocate everyone. See, first fit can allocate everyone. Whereas best fit, the name is best, but it cannot allocate everyone. So fragmentation happens. Okay, so best fit is always not best. Why the name is best fit? Because the fragmentation is less, internal fragmentation. Here I have written internal fragmentation. Now I will go for the worst fit. Maximum wastage, or you can say internal fragmentation, right? So let us draw 50, 150, 300, 350. Now the partitioning is fine. 600, right? Sorry. Okay. Requests are 300 worst fit. Any fit 300 cannot be fitted within 150, right? Next, I have P2 as 25. Worst fit means here I have 50, here I have 125. So here if I give this, then maximum wastage 125 wastage. So this is my worst fit. Best fit mane here I would have adjusted, but worst fit means maximum wastage portion will be allocated. P3 125. Now here I have 50, here I have 125. So here only I have to give best, worst, anything. Last P4 50. Oh yes, I have a P50. Okay, so see, first fit and worst fit both can accommodate all four process, right? But best fit cannot, because it means to give perfection, it has just lost the game. Fine. So external fragmentation happened. So we are having this problem of not allocating process number 4. Fine. So I am using variable partitioning. So within one partition, I am able to allocate both the processes, right? So just go through them once. First fit, wherever you find the place from your left hand side, you allocate the value. Whatever is the fragmentation, we will look it after that. Best fit, we will try to minimize the internal fragmentation. So best possible fragment, we will try to incorporate. And what is worst fit? Wherever I am likely to get maximum wastage, there only I will be assigned. So while I was trying to assign 25, here 50 was remaining, here 150 was remaining. So if I allocate in 50, 25 will be my wastage. If I allocate in 150, 125 will be my wastage. So I will go for 125 wastage. Is it clear? Worst fit, right? So this is my variable partitioning based memory allocation. Fine. Next, if the same thing I try using fixed size partitioning, then what will happen? If I try using the fixed size partitioning, then what will happen? In fixed size partitioning, if suppose I have like one particular, this particular one cannot be done like this. Means if suppose I have more than 50, then that cannot be allocated, right? So like don't get into those much details, just understand these 3 fits. Okay, fixed variable use kore ar korte hobe na, because it will be a bit complicated and you don't require this for your interview purpose. Like for university mathematics, you may need, but right now you can just omit. Fine. So this is your just remember these 3 fits: best, worst, and first fit. Okay, just these 3. Next, we will go towards the concept of paging. Next concept from where you can get question, we are going into that paging. See, you have your processor. Within the processor, you are having your registers, right? Here you have cache. Here you have main memory, right? Fine. From here, you have secondary storage. Fine. So this is your way of storage. Now, we have a concept of virtual storage. We have a concept of virtual storage. What is it? The data transfer time from the secondary memory to the processor, if made fast using this cache or something that we don't know as a user, we have the illusion that there is a infinite set of memory. Main memory is of infinite state. The user knows that I have RAM and ROM, and from there all the data is coming. But actually the data is coming from secondary memory, suppose. But as I have cache, in advance I am taking the data and getting it stored. So the process of data transfer is becoming very fast. Fine. Based on this, we have the concept of virtual. Virtual means something that does not exist. So user thinks that everything is present in main memory, but that is not your actual case. Fine. So what is actually virtual storage? This illusion that we are having, that we have infinite storage, everything we are having in main memory, this concept is coming from virtual storage. Okay. Now, we cannot say directly that your secondary memory is your virtual memory. Cannot directly say it like that. But yes, the concept of data transfer is fast to the processor because of cache. But the user will not understand that I have cache and so my process is fast. It will think everything is present in my RAM and ROM. Not in ROM because ROM is not capable. So everything is present in my RAM, main memory. So RAM, I have only suppose 8 GB of RAM and I have so much of data. No, data is actually coming from secondary storage. But because of your cache, the process is becoming fast. So this total concept is named as virtual storage, right? So secondary memory and virtual storage is not always same, but you have to include the process of being fast, which is done using cache, right? Now, while this data transfer is happening, the main memory is divided into number of frames. Main memory, I have segments of data, right? So they are frames. And in secondary memory, we have pages, right? In main memory, we have divided the main memory into number of frames, right? And the secondary storage into number of pages. Fine. Now understand one thing. When the processor is creating an address for data search, it will always search the data using address only. So when it is doing that, it does not know that I have a cache and main memory. So directly it generates a bigger address, the address space of secondary storage. This one we call as the logical address. So the address space of virtual storage is named as the logical address. But actually, we are having the physical storage address, right? Because once we are not into main memory, we cannot work. We cannot communicate with the processor. So processor does not know about anything. It uses the logical address. But the physical address is the address of your main memory. Now, we have to convert this logical address to physical address. Logical address is what? It is made of pages. And physical address is made of frames, right? So logical address is having the page numbers in it, and it has got an offset, data offset. What is it? Suppose if you think this is your secondary storage, then there are page 1, page 2, page 3, page 4, likewise. In each page, I can have more than one set of data. Suppose alphabets I am storing. So in one page, will there be only one alphabet? No, there can be multiple. So the position where the data that you are searching for is present in your page is the data offset, right? So logical address is made up of page number and data offset. Physical address is also made up on what? Frames. So frame number and data offset, right? Frame number and data offset. So what we have to do next? Convert this page number to frame number. How you can do that? See, whenever a data is coming from the secondary storage, it is coming in the form of page. But we don't want page in my main memory. We want the frame number where I can store it or where it is already stored. So I have to convert my logical address to physical address. This process is named as paging. What is paging? Logical address to physical address conversion is named as paging, right? Now, how it is being done? How this paging is done? See, if I have page and if I have frame, then in your operating system, we maintain a page table. where page numbers are mapped to frame numbers. Page numbers are mapped to frame numbers. There are multiple, right? So processor generates page number and data offset. Page number is being searched here. Okay, just give me a minute. I'm having a call. Okay, so just understand this page number is searched in the page table. Corresponding frame number you will get. Using this, you form a frame number and data offset, that within the frame where is your data. This becomes your main memory address. This becomes your physical address. So your main memory address. So this is your logical and this is your physical, right? So this is your main memory. Fine. So once you get the data, you are able to work. Fine. So this page is named as, this process is named as paging. So this is a data structure linear maintained by the operating system, right? So this is your paging. Fine. I hope it is clear. Next is, there is another method of this conversion which we call as segmentation. I hope you have learned of segmentation error, right? So I hope you have heard of, you have done a lot of programming. Segmentation error you get, right? So that is a type of address conversion error. Fine. So I will just discuss that, but before that, I will just give you 5 minutes of break. Remain in the meeting. I'm just coming back within 5 minutes. Okay. Okay. So the next one that we have is the segmentation, right? Now, when we have segmentation, how it is different? Suppose, what if the page number that is given to you, means given for search, is different for, means it is not different for, but it is not present in your table that is present. So how can you find that out? Suppose the processor is sending a logical address which is 52. We have a concept of a limit register. Limit register, what is it? The checking will be done here that whether your logical address that is sent is greater or lesser than your limit value, like array. Suppose I have an array of size 10, but I want to search for an element at the position 12. Is it possible? No. So that type of checking is done here. Suppose my total validity of the memory space is 100. Suppose limit register value is 100. So it will be checked here. 52 is less than 100. You will have either yes or no. If it is no, then you will get the segmentation error that you more often get while you are doing programming, right? If it is yes, then how the value will be found out, how the address will be found out? We have a relocation register. We have a relocation register. The value of the relocation register will come and get appended with this 52 logical address value. 52 will come here. Relocation register value will come here. It can be n number of any value to evolve your physical address, right? So this is your memory from where you can get your physical address. Suppose this is the place where your physical address is lying. So from here you can get your data, right? So this is your segmentation, right? So in segmentation, what we have to remember? We have to remember the value of the limit register and the value of the relocation register. Now, relocation register value is fixed for one program. So relocation register can be treated as a base register, suppose. My means base of your array index, right? Suppose it is 0, then 52 means the 52th position. At the 52th position, we are getting the value. Fine. So 0 plus 52, that type of your relocation register. Fine. Now, there can be a question that if my logical address is suppose 500, limit register, suppose logical address 500, 520, 700, like 825, 1128, these are my logical address values, right? Suppose the limit register value is 1000. Fine. Question can be, can I convert it to physical address or not? Yes or no? This is less than limit, so yes, less than limit, yes, 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 no. If I ask what is the value of your physical address, what is the value of the physical address, then you need the value of the relocation register, get it appended with the possible values of the logical address. right? So this type of question can be asked to you. The paging segmentation can be asked to you. These concepts can be asked for, right? So these are the more or less things that you will have from memory, right? So more than this may not be used. So you have one concept of TLB, translation look aside buffer. What is it? From your page table, the value, suppose your page table is full at a time. Suppose all the page numbers and frame numbers that the memory is using, everyone is fetched and the table is full at a point of time. At a given point of time, everyone is full. Now, a new page request is coming which is not present in your page table. What you will do? You will be replacing an existing page. From the page table, you will replace an existing page. For that replacement, we have the algorithms like first in, first out. So the page which has came first in the data structure will be replaced first. We have least, recently used page. So the pages that are present in your page table, the one that is not used for longest period of time will be replaced. We have optimal page replacement policy. The pages numbers are given. The request chain is given. Suppose 1, 2, 7, 11, 13, 5, 8, 19, like this. Suppose I am at this position that I need to insert, and I have here present 11, 13, 5, 19. So which one I will replace and insert to? The one which is farthest away. The one which is farthest away. So 19 is farthest away, so that will be replaced and 2 will be inserted. This is optimal page replacement policy. So replacing a page from your memory is not difficult. We have the algorithms. So algorithm names like FIFO, LRU, OPR, these names you must know, and the policies, but no one will give you the problems. But what is the translation look aside buffer? Now this 19 is getting replaced, right? So just a copy of the page table, not a copy, but just the same structure is maintained, which is the TLB, where the recently replaced data will get stored. Like in cache, the recently required data we are storing frequently used. Similarly, in TLB, from a page table, the ones which are getting recently replaced will get stored. Okay, so that is the concept of TLB that you must know. Fine. Page table, if it is full, if I need replacement, the replacements are getting stored into your translation look aside buffer. Okay, so that is the concept. Now next, I will quickly move into the disk management. Right, so I have more or less 15 minutes, so let us see whether I can complete within that. So in disk management, the only thing, disk management means we are talking about, memory management means I am talking about main memory management. Disk management means I am talking about the secondary storage management. Secondary storages can be of different types, different names. We do not go through everything, but what you require from this for your purpose, there are some scheduling algo which we require. So what is the scheduling algo? Suppose there are some disk requests coming in, at which sector, I suppose you have the idea of this concentric sectors. So if suppose these are the sectors, right? So partitions I have drawn. So on this, you have data like this, you have data, right? So which portion is accessed, that request is coming in. Which after which will be entertained, like process. which after which will be entertained, that is being done using the disk scheduling algorithm. Okay, so I will just take one example, and I will show you using same example. I will show you using different algorithms, right? So that you can find out what is the difference, right? So just I will write down the request, disk request 98, 183, 41, 122, 14, 124, 65, 67. Okay, from your book only I have taken this. Now let us see that what are my algorithms possible. First one, easiest one that we have in every case, FCFS. What is, if this is my question, then another thing is required, that is current position of read-write head and direction, right? Read-write head means the one which will go to this file, then this file, then this position, these things. Suppose that is given as 53, okay, and direction is upwards, right? So when required, I will use this. Now, when I go for FCFS, see, the disk is round, but we do not show it round. We just draw a straight line. From 0 we start. We have highest as 183, right? So suppose we take the highest one as 199. Okay, the points that are given I will mark. So 90, let us start from the smallest. 14. 14, then 41, then 60, 53 is the point, right? So 53, 65, 66, the side by side, sorry, 67. Then you have 98. Then you have 122, 124, 183. Okay. Now, if I follow first come, first serve, then again I will start from my left hand side and I will go to the right hand side. And I will just show the arrowhead. So, I am right now at 53. So, I will go to 98. That is the first request. Then 183. Then I will come to 41. 41. Right? Then I will go to 122. You can drop lines also, but I'm not doing that. Then 14. After this, 14. Then I have 124. My God. Then I have 65 and 67. 65, 67. Okay, so this is your FCFS algo. Based on the request's arrival position, the request will be entered.